we'll start nevertheless. Okay, so I'm going to read out some of the doubt sheet questions. There was one question about the Armijo rule, so it's okay. So question is, can you give a better intuition for having C1 in the Armijo's rule? So the Armijo rule is, you can see it in front of you right now, right? What did it say? That the function value should be below the linear approximation of the function, but not exactly the linear approximation of the function. We modified the slope to be this orange line over here. I put the C1 to reduce the slope a little bit from the original slope of the linear approximation. So the intuition behind it is, as I mentioned in the previous class, that I can have a little bit more relaxed criteria. The most relaxed criteria would be C1 equal to 0. That means the function value should just be less than the value of the function at xk. That's really, I mean, that is anyway going to happen because of sufficient decrease and it being a descent direction. So we are trying to, this is like a tuning knob you have in your hand. There is no theoretical guarantee or proof that it should be some value or the other. This is something that you will locally use to fine tune your rate of convergence. Okay, so there's nothing very deep about it. Choosing alpha. Choosing the perfect alpha implies phi dash alpha equal to 0. This results in taking a step that blows past our minima, and then we turn around to take a small step. Well, if you chose if you chose the perfect alpha, you would land up at the correct solution, right? So you will not go past. But this is always an issue that if I choose too big of a step size, I can go past my solution, in which case I need to come back. So the backtracking line search algorithm which I gave you, it works on that principle. I start with a large step size and start walking back until some of the conditions are satisfied, and I say, okay, this is a good step length. I think there was a small typo in the curvature condition, so let's look at the curvature condition. Slope of the linear approximation at 0 in the at xk instead of, well, I think it's correct. It's exactly what is written here. If we do not know the exact function, that is all the data points that we have are x comma fx, then we do not know what f is. Why not just keep track of the minima while collecting all the values? Okay, question is clear? So we said that when we spoke about the intuition over here, which was, I think, this graph, right, that we don't know the shape of this graph because this graph is expensive to calculate. So the question is, if we do not know the exact function and we only have the data points, why don't we just sort of pick points and keep track of the minima? Does the optimization part come when we model a random function and compare the minima as a metric of how good the function approximation is? So and related is, I do not understand the point of alpha. If function evaluation is expensive, then using derivatives Hessians as a condition to check if alpha is a good learning rate is contradictory. If the bounds on alpha are found by function evaluation, we might as well evaluate the function at a lot of points and find the minima, right? As always, as they say, the devil lies in the details, right? Now, if your function, if for example I take 3 points, so supposing I pick 3 random points, and with 3 points and a function of single variable, what is the best I could do in terms of fitting a polynomial? 3 points. I can fit a parabola, right? Now, if I can fit a parabola, so supposing, let us say, right, so I pick 1 point here, 1 point here, 1 point here. Now, with these 3 points, I fit a parabola, and I automatically know that this is the best point, right? This is the minima point. Now, if I were only taking function values and samples, it will take me forever to reach this point, and even when I reach a point, I will not have any guarantee that there is no other better point available. So one of the assumptions that we are making throughout this course is the functions that we are dealing with are continuous, and not just continuous, they are also differentiable. So calculus gives us nice ideas of smoothness which we can use. That's why a few function evaluations, like 3 function evaluations, is giving us a good approximation, second order approximation. So in this case, it's justified. Okay, going purely by function values is always going to be more expensive. without any guarantee that you've hit the correct point, right? So it's a lot of trial and error, and we don't want to rely on trial and error. Okay. So the sort of underlying assumption to be kept in mind is continuity and differentiability, and calculus gets you a lot more than just simple function evaluations. So does that clarify whoever this students the doubt was? Okay, I guess. Okay, so today we are going to talk about line search, the analysis part. Okay, convergence is what we're going to talk about. So let's write that down. Line search, analysis. Now you've already seen the backtracking line search algorithm, right? So the backtracking line search algorithm was basically, let's just recap that before we get into analysis. So the recap is, we spoke about backtracking line search. Which was basically, I have f of xk plus alpha pk. This should be, if I am taking the sufficient decrease condition, this function value should be less than what? Right. So f of xk plus c1 alpha grad fk transpose pk, right? And this was C1, and I am going to say repeat until this holds true, okay, and you keep updating alpha like this. That was our very simple update. It required function evaluations, okay, only one gradient, and that is this gradient at alpha equal to 0. Now, the second, okay, so if you look at the optimization literature, there are lots and lots of different tricks that people have tried instead of backtracking line search. Okay, so I'm going to give you just one more example, which I referred to just a few minutes ago, of another trick which people will do, which is that let us say that phi of alpha. Okay, we all know what phi of alpha is. Now I give you, for example, phi dash of alpha. I calculate this. I calculate this, and I calculate phi dash of 0. Okay, pick any alpha and calculate this. So this gave me 3 points, 3 different values of either phi or phi dash. What I could do with it is next is to fit a parabola, right? Once I fit a parabola, I could come analytically, I can come to the point at which that function is minimized, and I pick that to be my best alpha. So here I am not doing backtracking line search, I am doing quadratic fit, minimizing the quadratic function and choosing that as my best alpha. So this is going to be good as long as the quadratic approximation is good. So if I pick a very large alpha, it's not likely that the function is going to be a quadratic function starting from alpha equal to 0 all the way to alpha equal to some large number, right? So again I have to pick a reasonable number, right? So fit a quadratic okay. Once you get a hang of this idea, you can go a little crazy with it. I can take, instead of 3 points, I could take n points and interpolate a polynomial. Once I interpolate a polynomial, I can see are there multiple minima. I could fit a cubic, a quintic, whatever, and come to those points. So you will find variations of this throughout the literature. Okay. Now, as it turns out, all of these tricks are not going to fundamentally change the rate of convergence. The rate of convergence, as we will derive later in this lecture or possibly in the next lecture, is linear. There is nothing that you can do to beat linear. Okay. Okay, so let's now try to understand, first of all, does this line search method, for example, using steepest descent or gradient descent, does it converge? If it converges, at what rate does it converge? So I am going to draw a graph over here. A better version of that is on the class notes. Okay, I am going to try to draw it over here. So what I am drawing are the contours of the function. So what are contours? Lines on which the function value is the same. So think of them as cross sections of a hill, right? So this is one, this is one. So I am trying to draw something elliptical. Okay. And let us say I start at this point. This is my starting point. Okay. Now if this is the starting point, let us say that these contours are in such a way that this is, let us say, f1, f2, f3, such that f1 is greater than f2, greater than f3. These are the contours. So the function value is decreasing as I go down. So it's a little bit like a crater. So if I am at this blue dot over here, and if I were doing two things, let me do steepest descent or gradient descent, same thing, and I am doing exact line search. Let us take these two very simplistic ideas. Supposing I were doing this. So from this blue arrow, where would I go? Towards the center or away from the center? Towards the center. Any particular angle I should make with the black line? 90 degree, because we said that the gradient is the direction of steepest descent and the gradient is perpendicular to the contours. So I am going to land up something like this. Okay. I am going to go from here. Now when I hit this next contour, if I keep going on this, will the function value start increasing or decreasing? Supposing I keep going like this. After some point it is going to start increasing again. Finally when I come back to here, I am back to f1, right. So the point at which this is going to be minimized is, in this case, for example, when it hits the next contour. So when it hits the next contour, let us say over here, I take so this is exact line search. Let us say I have the computational resources to do exact line search, I got this. From here again I am going to head this way until, let us say, I hit over here. Exact line search, I hit the next contour. Pardon me? Pk is the negative gradient or steepest descent, right. So we are doing that. So I went from here to here like this, and so on, right. So let us take one more thing over here, right. And the next step from here, again I start kind of going like this. This is also 90 degrees. I end up over here. Okay. My drawing is of course great, but this is, if you draw it properly, this is roughly what it's going to look like. So what are the two assumptions that I made? One is Pk, which is our descent direction, is the minus grad Fk at each cell. So that is gradient descent. The second assumption, exact line search. So I always pick the correct alpha and arrived at my next point, right. So exact Why am I making the second assumption? Just to simplify my life. Okay. So what are the observations that you, let's note that down, it's quite important over here. What do we observe? Looking at this, assuming you're following my drawing, what are the kind of key observations that you can make looking at this? So the true solution was sitting over here at the center over here, right. So what can you say about the trajectory? Is it straight line or zigzag? It's a zigzag trajectory. In general, it's a zigzag trajectory. So it's the first thing that we observe is zigzag trajectory, which is kind of counterintuitive, because when we said steepest descent, we said we are going in the direction in which the function decreases the most. Then you would think it would just be smooth sailing into the minima of the solution. But what is actually happening is I am walking some steps. I mean, every step that I am taking has some component in the wrong direction. I want to move towards the center, but I am going up and I am going down, I am going up and I am going down. So there is a zigzag kind of a behavior observed. What else can you observe? What about the step sizes? What do they seem to, are they the same, increasing, decreasing? The step sizes seem to be decreasing. Any other observation? Each step is perpendicular to the previous step. I go this way, then I am taking a 90-degree turn, then I am taking a 90-degree turn. This is, I mean, assuming you are trusting my drawing, this is that each step is perpendicular to previous step. Right? These are just observations based on looking at this drawing. So, I mean, we shouldn't take this the observation just on face value. Let's try to prove at least one of them. The most significant one is the third one. Let's try to prove it. Yeah, question. If we change the starting point, then the third point may not hold. So you have actually gone ahead of what I want to say. I will come to exactly what you have said. Okay. What he is saying is that if I started, for example, if I started from here, then 90 degrees is going to take me which way? If I start from here, such that 90 degrees is pointing straight over here, right? For in one shot I reach the global minimum, I mean the local minima of this problem. Why is that? Because every time I go cross any of the function contours, I am at 90 degrees, I keep going and I reach over here, right? So this is an example where, of course, starting point is critical, that is what it is telling you. Secondly, it is telling you that there are some special points where I can reach in one shot, and that strongly depends on the type of contours I draw. If it were a more complicated contour, maybe such a trajectory may not be possible. Okay. But you can see that there is a geometric flavor here. Supposing the contours were not elliptical, but supposing they were circular, then would it matter where you start? Any point you start, you zoom right in, right? Now, when will I get a circular contour, when will I get an elliptical contour?
The quadratic form, the matrix, if they have different eigenvalues, you will have elliptic form.
Okay, so let's put it in geometrical terms, we will get the details later. But if I have the curvature is the same everywhere on the object, right? That means it's like a perfect sphere almost in n dimensions. Then no matter where you start, you end up over here. But if the curvature is different in different directions, then what will happen? Some places will, I mean, it will look elliptical. Then the starting point matters, right? What is curvature related to? Gradients also. What else? Hessian actually. The curvature of a curve, when we talk, we are actually referring to the second derivative, right? The gradient is talking about slope, but the rate at which the slope changes is what is going to give me curvature, which is actually Hessian. So there is going to be some geometrical insight that we will extract from the Hessian of the problem, which we will come back to later, that when am I forced to do zigzag and when am I not forced to do zigzag. Okay. So let's try to prove this guy. Okay, surprisingly easy proof. Okay, so I'm going to write a shorthand notation for the step between 2 points. Sk is what I'm going to call it, which is simply this distance. Okay. Now, having written this Sk, in math, how will I write condition 3? What is the mathematical equivalent of condition 3? Sk transpose Sk plus 1, for example, should be equal to 0. That is what I want to prove. There are, I mean, all sorts of variations of it. I can write it as Sk plus 2 transpose Sk plus 1 equal to 0, whatever, right? Whatever makes my life easier. So remember I wrote sk plus xk plus 1 is xk plus alpha k pk. So, together from here what will sk be? Alpha k pk simply, right. So, okay, so we can keep this. So, we have got one expression for sk. Now, what was my phi of alpha? This was simply not fk, xk plus alpha pk, right. This is the one dimensional function that we had defined from earlier, and when I took d phi by d alpha, d phi by d alpha, can someone recall what that was? Gradient of this thing transpose pk, right. This is what we had done last time. Simple chain rule had given this to us, right. So, what was, when I made this set of contours, what was the one of the assumptions was exact line search. What is the meaning of exact line search in terms of d phi by d alpha? Has to be 0. That is the condition for exact line search, right. So, exact line search implies that d phi by d alpha equal to 0, which in turn implies that grad of f x k plus, now I will put alpha k because it is that alpha k transpose p k must be equal to 0. Agreed, right. So, can you see how we are almost there? This was my expression for sk, right. So, now let us substitute in over here, right. So, what will I get? This is the expression that I want to prove, right. Now, sk plus 2 transpose sk, what will that be? Let us use this expression. So, this will, what will I get out from here? Alpha, I am going to use this expression over here to substitute into here. So, what will I get? What are the alphas that will come out? Alpha k plus 2, alpha k plus, sorry, this should be plus 1, sorry, alpha k plus 1. What else am I left with? pk plus 1 transpose pk, okay. What else? Can someone see what is happening over here? Are we almost there? What is pk plus 1? We are doing gradient descent, right. So, pk plus 1 should be minus grad f k plus 1, which is nothing but minus grad f of xk plus alpha k pk, right. So, now this expression over here I can substitute over here, right. What am I going to get? Alpha k plus 2, alpha k plus 1, I am going to get a minus, I will write that minus outside, grad f of xk plus alpha k pk transpose into pk, and this is what? We did exact line search, right. So, therefore, we have this expression over here, right. So, there are just two ideas that I used over here. One is the definition of sk, you can call that equation 1, which gave us basically this. The second idea was we are doing exact line search, therefore, this was the second condition, that is it. Because I am doing exact line search, I got this. Because I am doing gradient descent, I got, you can say this is expression 3, I got expression 3. I just combined these two ideas of exact line search, gradient descent. Combine this and you can see that every subsequent step is perpendicular to the other step, right. So, remember, if you were to do backtracking line search, Supposing you write your own MATLAB code, in fact there will be one of the tutorial problems where you write your own MATLAB code, and you choose to do backtracking line search, and do you expect that the trajectory of your points will be zigzag? I hear one yes. Any other responses? I am doing backtracking line search. So look back at backtracking line search. Will I expect a zigzag trajectory of my points? That is the starting. In backtracking line search, I start with a large alpha, keep reducing it until, for example, sufficient decrease condition is satisfied. So how many people think I will see a zigzag? Zigzag, yes. Okay, let me make it a little bit more specific. Zigzag with perpendicular steps. Will I see perpendicular steps? Not necessary. Why? Because there is a very specific reason why I am getting 90 degrees. That 90 degrees is coming because of exact line search, which is equation 2 over here. Equation 2 is what is assuring me that this is going to be 0. So I may see zigzagging, but I may not see 90 degrees each time, right. So this is, it's more like a textbook illustration, because in practice almost no one would do exact line search because it's expensive, unless your function was analytically given to you, which is more like a homework problem rather than real life, okay.